Now, the other one is I will make this link to is what I call here the new energy economy. Some people may call it the energy transition. I'm not sure if that term is too appropriate because it's more of an evolution than a transition, but I'll get to this. First, a little bit housekeeping here to agree on terms and what to expect. So you may hear fractures, structural geology, or maybe fracking, something like this, and you may probably eyes may glaze over and then you're done. So fractures, you may associate something like this here. On the left side, you have a typically joined with a plumo structure. You may have seen this in the field. On the right side, this is actually taken from enchanted rock, cracks in the ground, in this case, the granite. Very narrow apertures, I emphasize this right away. And there may be some slip on it, and then we may call them faults. I don't really distinguish here. I'm more worried about what we call opening mode fractures, but they can have some slip on it. Okay. So those are your garden variety fractures. And then you have something like this, and you may call them veins. They are also fractures, except that they are filled with some cement. And on the left side, it is it's a place in southern France. It's calcite cement. On the right side, it is actually Min's field area in the White Mountains in California, and it's a quartz cement. And not only are cemented, they also have those really wide, large apertures. And that is something I will dwell on over and over again in this presentation here. Because, let me say this right here now. Going back to my PhD days, I took a class in fracture mechanics by a very famous material scientist. He's actually the most cited material scientist with an H index of 160, 70, something like this. Crazy number of publications. And what I learned in this class was a really good class, but I could not relate this to this. I could not. I was working on the Monterey Formation, which I'll show a picture in a moment, and it's different. So I thought, what's wrong? So this is just two other examples here. Similar fractures with wide apertures. On the left side is a granite diorite in the Sierra Nevada, which is, you would call it a little dike. And below that is actually, that's a tape measure here, because we were measuring the aperture distribution along another one here. But this is a one that you can see plainly. And this is something totally different. This is a rhyolite flow near Mono Lake, also in California. And those are opening mode fractures probably when the rhyolite solidifies at the very top, it's cooling, but the lower part is still viscous and flowing, and then it stretches the upper crusty layer and it pulls it apart. So those are little mid-ocean ridges here actually. And they also have those wide apertures, but totally different mechanism, right? So this is a picture from the Monterey Formation. It's a coastal exposure, so you have some crater there for scale. And it is of interest because it is what's called a porcelainite. It's initially deposited as diatoms. And the diatoms are opal A, which is very reactive in the subsurface. It's made stable. So it goes this transition from opal A to opal cetine and the quartz. So it undergoes very complex diagenesis, and then there are other mineral phases that undergo diagenesis. So it's very reactive, geologically speaking. And I always thought, so maybe those wide apertures have something to do with chemistry. And I came from structural geology. I didn't know much about chemistry, but I was stuck with this advisor, Jim Bowes, who was a geochemist. And he said, well, if you want to work with me, you can work on fractures, but you have to look at geochemistry. So I did. And that got me started on this journey that I will be telling you today about. So fractures with large apertures in a material that's very chemically reactive. It did not match what I was learning in the fracture mechanics class, which I'll get back to, because in that case it predicts really narrow apertures. And so even then the hypothesis was, and this is slow research, okay? Working on it for decades, on and off, I should say, on and off, more off than on. That the wide apertures, and as it turns out the shapes of those fractures, is actually related probably more by chemistry than the mechanics. So that's the hypothesis. There's a working hypothesis here. And I will definitely, well, I probably hope to convince you that this is true, actually. Reason this is important is apertures really are a big control for fluid flow in fractured reservoirs. It's also connectivity of fractures. But for what we call open fractures, which have an inlet and outlet, it's the for system fractures, the cube of the aperture, right? So it's aperture matters. And it matters in oil and gas reservoirs, like the left image here is the Monterey Formation. It is considered a shale because it's so fine-grained. So it's, as I said, it's this opal A, opal CT diatomaceous material, but clays as well. So there's a clay-rich layer, and this is a more silica-rich layer. And it's heavily fractured, as you can see, and there's oil oozing out of the cliffs. Natural oil. This is not some oil and gas production residue there. This is natural oil seeping out. The oil is seeping in the seafloor. I did ROV dives with the Monterey Aquarium Research Institute. That's bubbling up. The gas is bubbling up, and the oil is kind of droplets moving up, making a big mess in the beach. So this is actually naturally seeping out of the formation, which is generating hydrocarbons today. It's an active source, and it's being produced at the same time. So it's replenishing, actually, to some degree, what they're producing. So it's important for this. So this is considered a conventional reservoir because it doesn't have to be hydraulically fractured. The one on the right side is a tight gas sandstone reservoir in Alberta, Canada. It has fractures in it, but they are not abundant enough, so this needs to be hydraulically fractured for the natural gas to be produced. Okay. So fractures are relevant to both types of oil and gas reservoirs. I had John Major was working, that's him from behind here, on a CO2, natural CO2 seep in Utah, and we were interested to figure out how the CO2 can react with the rock and that affect fracture properties. So you have, this is in the vicinity of the fault, you have lots of fractures in the vicinity of the fault, you have those halos. The halo is in part bleaching, but also carbonate precipitation in the shale. And that's one of the, there's a wellbore there that's leaking CO2, but then there are also natural springs that have CO2 bubbling out in the vicinity. So we worked on a CO2 application of all of this, and Owen Callahan worked on a geothermal application of this. This is Dixie Valley, Nevada, where there's an active operating power plant, a geothermal power plant, and fantastic exposures just a mile away from the power plant. It's a range front fault, and with great exposure. That's Owen, that's his outside advisor, Nick Tavatzis from Temple University, and there are fantastic fractures in the footwall of this fault. That may actually in part predate the geothermal system, in part they are synchronous with it. The complex tectonic and complex structural history, for sure. So, clearly applicable to a wide range in applied fields where geologists can have an input. So I put two slides in there to give you a little bit of an outlook. So the bad news up front here, this is from the Energy EIA, Energy Information Administration. It's a government entity. And they come up with a yearly report. This is actually not the most current one, but the current one doesn't have the plots that are convenient as those. So this is from last year. And the bad news is that the best prediction they can make until 2050 is that oil and gas is not really going down, you know, if you look at this here, petroleum generation, production and natural gas. You know. What's going down is coal, and renewables are going up, right? This is US consumption by fuel source. Then they break it down for electricity. They have nuclear remaining constant here. And then I put this in because it actually shows geothermal. This is just renewable electricity generation. It's just a subset of the whole thing, but geothermal is a very small part, and they don't predict this to go up. I'm a little bit sad to see that, because I would think that geothermal has much more potential, but there are technology challenges there to really produce geothermal everywhere, not just in a few spots in Nevada and California, but actually in the mid-continent and eastern US, right? You have to go either very deep, or you have to have very efficient operations to work with fluids that are only 100 degrees centigrade or 120 centigrade, right? So there are technology challenges there, and some of those challenges are actually fracturing reservoir. If you go into the basement, there is the project, the Forge project in Utah. They tried to figure out how to hydraulically fracture the reservoir to produce the hot water for geothermal energy. This is not trivial. And then there's the carbon sequestration, where also fractures could be important. And this is kind of hard to see without glasses, but this shows here, this is from Wood Mackenzie actually, how we can reduce our carbon footprint globally and different techniques of doing it. And CCS is one small portion of this. So it's not the solution for everything, but it could be a contributing solution. So, and then there's hydrogen, which is not on those figures before, because it's not an energy source, it's an energy carrier. So you have to, except for natural hydrogen, which we don't know how important it is. But for the most part, people consider that hydrogen is being produced by electrolysis or methane steam reformation, and can be used for all kinds of purposes. As a feedstock, as to produce heat, to drive vehicles with fuel cells, to making other fuels out of it, you name it. Ammonia is a big use for hydrogen, and you can store it, and you can store it in the subsurface. The reason this is what we are working on, hydrogen storage in the subsurface. The reason this is potentially significant, currently the only way for seasonal storage is natural gas. That's the only way we can store energy seasonally for heating in the winter, or in the southern states, maybe cooling in the summer, right? If we move away from fossil fuels, then we may have to come up with something else. And energy storage becomes more important with more wind and solar, because that's daily fluctuations and seasonal fluctuations. So energy storage will be a bigger issue, obviously competing with batteries short term, but this is longer term, right? Months and couple of months, and maybe even multi-year, right? And hydrogen could have the advantage here to replace natural gas. And there are some predictions here for, but if you look at different projections, how this will evolve over the next 30 years, again, they are all over the place, you know. So it's a lot of input parameters here. Just a few words here about hydrogen storage. There are two ways of doing it. One is salt caverns, solution caverns, and this is already being done here in Texas. And there are some fracture relevance there, but primarily we're interested in storage of hydrogen in porous reservoirs, either depleted oil and gas fields or aquifers. And then you have to worry about the caprock integrity, because hydrogen is very volatile. And if the caprock has fractures in it, then it would go in the air. And it's actually an indirect greenhouse gas. You don't want that. This map shows the distribution in the US of salt layers and depleted oil and gas fields and saline aquifers. So the choice between those different techniques may be controlled by geology. And it is currently, this is natural gas storage in those different types of reservoirs. It is controlled by geology. So this would also apply to hydrogen. So this is maybe one of the big important slides of my talk here today, because it's trying to make the case that for all those different energy systems, fractures and faults can be important. So I was talking about conventional oil and gas. It's not going to go away anytime soon. I talked about unconventional oil and gas, hydraulic fractures. It's a little bit different than natural fractures, but also fracture related. I mentioned geothermal. And with the enhanced geothermal, which is what they're trying to do at the Forge site in Utah, it's not just getting a fracture from one well to another well, because that creates what we call a fast path. You basically just inject cold water and produce cold water. What you need is actually a distributed fracture network, because you want to expose the cold water with a lot of hot rock, just like a radiator, right? And creating such a fracture network is really tricky. And I don't think they know how to do this yet. We'll see, because they will, in a few years, we will know how the Forge site is producing. There's another site in Nevada that's going on right now. Then I mentioned already carbon storage, caprock, right? You don't want CO2 escape. Same thing with the hydrogen storage, caprock, well integrity, there are fractures as well, faults too. And then the one I haven't mentioned so far is nuclear energy, it's projected to remain steady. There is this thing about the nuclear waste, right? This is totally, nobody talks about it. Just blind us, nobody wants to talk about it. But high-level nuclear waste could have a containment issue, and factors are also relevant for that. So, that's the, I'm concluding the big significance, real part of my spiel here. Now, back to the, well, that sums it up here. Sorry for apologies for this just text slide here, but we need to distinguish, and I've done this already, natural fractures that, like the ones in Tall Mountain Granite, right? Then hydraulic fractures, which are obviously engineered in either oil and gas or geothermal. And also fractures that are resulting from human interaction but are unintentional, right? So they're not really engineered, they're accidental fractures induced. And that could be by injecting fluid in the subsurface at the pressure that's too high, and then the whole thing fractures. That's the case where we're concerned about CO2 storage or hydrogen storage. Also, I'm not talking about faulting here in my talk, but we've worked on this, fault reactivation with injection. Earthquakes, big topic was a big topic in the Fort Worth Basin in Oklahoma. Now it's all in West Texas. Nobody lives there, nobody cares, right? Magnitude 5s. That's not, I lived in California for 14 years. Magnitude 5 is pretty interesting. So that as well, right? So natural hydraulic fractures, and then those unintentional fractures, which could be existing natural ones or purely new ones, right? Okay, so get back to my lecture as a grad student. That's what I learned there. Basically linear elastic fracture mechanics. And it's summed up by this equation here. There is a material parameter. If you apply a stress to a material of an existing strata fracture of a certain length, and you exceed the load, then the fracture will propagate. It does not tell you how fast it propagates, just tells you it will propagate, right? And that's purely mechanical, okay? Brittle failure. The variance to this could be not just elastic, it could be elastic plastic, viscoelastic, whatever, you know, but it comes down to the same thing. Now, that's the other side to the whole metal here, is chemomechanical fracture growth. So chemistry is involved. And there are a couple of options here. The first one is that the reactions are just weakening the material a little bit. So it's still a mechanical fracture, but it's weakened by the chemical reaction. And that's usually, and it could be dissolution, hydration, different reactions. That's usually put under the header of subcritical fracture or stress corrosion fracture. Okay. Then the other one here, at the lowest part here, is when the reactions are actually driving the whole thing. And I will show you, Mint and I were able to produce this in the lab. Okay, the reaction is actually driving the fracture. The stresses are generated by the reaction. And then maybe, and I made this term up, it may not, I haven't published this, so this may go away again, you know. But reaction modulated, so it's somewhere in the middle of those two, you know. So the rate is controlled by the reaction, but it's still the stress, obviously, you need to have a stress to drive the fracture. There's no question about this. So I don't know about this. So subcritical fracture, I talk a lot of this now for maybe 15 minutes, you know, because we have done a lot of work on this. And it's better understood than the other part, the one where the chemistry drives the fracture. And you're actually familiar with it if you ever had the luck of having a cracked windshield. Sometimes you notice that it doesn't shatter the windshield entirely, but the fracture gets long and long. Often, as long as you procrastinate, it gets longer, right? And then you have rain, and then during the rain, it actually grows faster, and then when it's dry, it doesn't. That's actually stress corrosion fracture, you know, or subcritical fracture. And in the lab, Zhao Feng, he actually used the glass slide to reproduce this, and put this in our testing rig. And this is velocity versus stress. And it's actually the log of the velocity. And typically, people plot the log of the stress, but it doesn't matter here. So you get this, as you increase the stress, the fracture becomes faster. And that slope here, that exponent here is used as the subcritical fracture index. That's kind of the metric we use to quantify how prone a material is to subcritical fracture growth. So in this case, it's a glass slide, but obviously we can do this with rocks. So that's the apparatus we use is benchtop. It's this big, and what it does is it's actually applying a stress. It's torquing the material. The sample is the size of a thin section. It's a thin plate with a groove on it, and it's being torqued, and and as it's being torqued, the fracture propagates along the long axis of that sample. Okay, so it's not, you know, like the triaxial experiments where you have a piston. This is a little bit. There is a piston, but it's torquing it. So there's a ball bearing here, and then the piston is pushing down here. And the nice thing is you can actually submerge this into water or brine or acidic brine, so we can actually test the effect of the environment. We can put plastic background and use dry CO2, for instance, to test what's the effect of humidity. The lab humidity actually has an effect on this. So if you use nitrogen or dry CO2, it's actually behaving differently than in the lab conditions. And then we can also heat it up to sub-boiling conditions. That's John Major doing some experiments. So this is some results of shales that we tested. 3 different types of shales that may be sealing shales, maybe not. You know, the Mancos maybe, the Woodford Marcellus maybe not so much, but we had to actually buy those because we need a fairly a good amount of material. It needs to be fresh, so outcrop material doesn't work. So it's quartz shale. At different conditions, room dry, in that dry CO2 gas, DI water, varying salinity, varying salt content, pH, and temperature. And those 3 rock types are very different in composition. One is very quartz rich, the other one is very calcite rich. It's almost actually a limestone. And then the Mancos is somewhere between. None of those is really clay mineral rich, because if they're too clay, then we cannot work with them. So there's a bias there, a sampling bias. So this shows the effect of just what we call water content, humidity versus saturated with water. And on the left, you have the fracture toughness, which is the measure of mechanical breakage primarily, and rapid breakage, and the subcritical index on the right side, which is the measure of subcritical fracture propagation. And you see that some materials are fairly insensitive to water content because they don't have any clays in it, but the ones that have more clays in it are highly sensitive to the water content. Even illite, interestingly enough, which is not considered a swelling clay, but still is sensitive to the water content. And then effects of pH. The carbonate-rich sample is sensitive to the pH, no surprise there. Not for the fracture toughness, because it's a fairly rapid process, but the subcritical index, which is a slower process, the material has more time to react with the acid, therefore it sees there's a pH dependence here. The subcritical index is lower at low pH than at high pH. And salinity effect for the Woodford, which has some clays in it, there's also that, you know. So it really depends on the rock type. The other thing I want to emphasize here is, when I started this, our carbon sequestration gurus at the bureau said, well, we don't think it matters much, because when we do batch experiments, the rocks don't really react enough with the brine or so. Well, that's because they put chunks in there, and they were thinking that it would permeate, or it's not happening, you know. But to have an impact on the fractures, you don't need that. All you need is the reaction to occur at the very fracture tip. So the volume that it reacts is minimal on the micron scale or millimeter scale, perhaps, you know. And as long as the fracture doesn't propagate too rapidly and the reaction goes along with the propagating tip, that's enough to have an impact, because that's what we have seen in our experiments. So you don't have to kind of dissolve the whole caprock in acid to have a difference on the fracture properties. All it takes is the little bit of tiny reaction to the tip, and we ascertained this by coating this sample with a hydrophobic agent. You buy this in the hardware store, and that makes sure that water has no access to the shale except the fracture tip. And now you may wonder, how does this really have an effect on fracture connectivity and flow? That is obviously something that one has to model, simulate, and this is a boundary element code that John Olsen has. It's fairly simplistic, but it's probably the best thing you can do to model the effect of subcritical fracture growth and fracture network geometry. And those are the three rock types. This is going from less reactive to more reactive. The low pH sample is at the bottom, the dry sample is at the top, and you see that fracture networks that are predicted here are getting more complicated, more complex. And on the right side is a little bit more difficult to understand here. So this is time, or not really time, it's simulation steps. So it's going up to 1,000 something. And on the vertical axis is normalized. It's a flow parameter, so that's the Darcy K. And for the different types of, for the three different rock types and the three different environmental conditions. And it turns out that as the fracture networks evolve, yes, so some get more complex, but some increase in permeability initially faster, but then they kind of remain low, versus in this case here, the dry one, which is the simplest fracture network geometry, nothing happens for a lot of time steps, and then it goes rapidly up, and actually it ends up with the highest permeability. So this is not very intuitive. You know, you think that most complex fracture networks provide more fracture permeability, but in this case, initially, yes, but then over time it flips, and then the simple fracture network actually has more permeability because it just goes straight through. So it's a little bit counterintuitive, but it has an effect on permeability according to those 2D simulations. All right, now just to show off, we have done a lot of testing, not just in shales, but this is a sandstone that John Major tested. And in this case, it's only dry versus wet, and wet is always weaker for fracture toughness and subcritical index. This is something we did also at this field site. We were testing sandstones that have been altered by reactions by geologic processes. In one case, bleaching, in the other one, calcite cementation, and there are differences in the fracture properties. The bleached sandstone is weaker because you dissolve the hematite grain coats, and obviously cementation, calcite, strengthens the rock. It's not surprising either. That's more shale work, kind of same story. And then Owen did a lot of sampling and testing for his geothermal, epithermal, hydrothermal field site. And there are different hydrothermal alteration reactions that if it is heavily silicified, then obviously it strengthens the rock. This is what he called precipitation dominated. This is plotted, different samples taken at a different distance away from the range-bound fault. The highest amount of silicification is right next to it. Those are the strongest samples. You go away, same formation, lower fracture toughness, and the subcritical index goes down as well. The other reaction is where you form a lot of clays, so it's actually weakening the rock. Form chloride and carbonates, and the alteration is actually weakening the rock. So it can go both ways depending on where you are. And there's some depth zonation of those reactions, so you can actually predict the fracture strength, and then also perhaps fault strength is a function of depth, depending on what kind of reactions you have. So this is relative to the starting, in this case, granodiorite, and different parameters here, the UCS that we measure in a triaxial apparatus, then the fracture toughness and the subcritical index. So depending on how those fracture properties are responding, what the loading rate is, different parameters may be actually the relevant ones. So you can make some predictions with this information in terms of how strong the rock is as a function of depth in your epithermal field, and how fracture networks will evolve. Now, going back to the story of aperture size and shape, okay? So this was all subcritical fracture testing, fairly well understood. There's a fair amount of literature on this. We know that fluids can react at the fracture tip. It can weaken the rock, it can strengthen the rock. Has primarily an effect on velocity of the fracture, which can also affect connectivity at the end, you know, so it's not just how fast it goes, but how they interact, fractures interaction. But now I'm moving back to single fractures, and looking specifically at aperture and shape. Now, back to this story of my class lecture, LEFM fractures. They are predicted to be very narrow, and I'll show this in a moment. And the question is, where can we see this? So an outcropped joint in the Town Mountain granite is a little bit deceiving, because when we talk about LEFM aperture, it's actually the aperture when the stress is being applied, when something is pulling on it. But on the Town Mountain granite, that stress is probably gone. So it would close again, right? So this could be misleading. So there's actually, in the geoscience, we don't really have good examples of a true LEFM fracture that would show the aperture while it's being stressed. Maybe in a tunnel on the ceiling and it's about to fall down on you, right? So I don't want to measure the aperture there. One case though is in hydraulic fractures, because they inject proppant, and the proppant artificially keeps the fracture open even when the fluid pressure goes away. And Julia Gale was involved in this large DOE project where they actually cored hydraulically fractured shale, and then in this case imaged it, and they see the hydraulic fractures with the proppant in it. So that gives you an idea. I don't have a scale on here, but this would be in the order of a millimeter, so, right? And then they also looked at the core samples to see the proppant in it. So that's the proppant here. It's like a mush, a slurry. And in some cases, the proppant can be packed a few millimeters wide. It's probably local widening of connecting fractures. But generally speaking, those fractures are a millimeter, so very narrow. But then we have natural fractures that look like this in the subsurface. So this is a tight gas sandstone in East Texas, Travis Peak Formation. That is in millimeters here, okay? Centimeters here, and that's in inches. So those is massive wide open fractures. That's Barnett Shale, the Delaware Basin, also partially open fractures. So they do exist with wide apertures. And then the extreme case is something let's go back now, 20 years. I was working on silicious shales that has been baked naturally by burning hydrocarbons. So the hydrocarbons are seeping up naturally, lightning hits it, or some bushfire or something, and the hydrocarbons start burning, just like a coal seam burning. And this can go on for years and decades, actually, in the subsurface. So it spreads around. And what it does, it bakes, it's like a brick, right? Bakes the rock, the shale, and it produces fantastic fractures as it does that. So really, really nice open fractures. It's called clinker, and it's pretty common in Southern California, actually. Looks red in the landscape. So, since I've talked already so much about linear elastic fracture mechanics, there is this equation here that predicts the aperture as a function of the fracture toughness and the elastic properties of the material. And regardless of if you use some realistic elastic parameters, and fracture toughness doesn't change much, it's pretty uniform for all rock types, it predicts certain apertures as a function of length through those solid lines here, with the dashed line. So this is length here on a log scale, going all the way to 10 kilometers, and aperture from, well, there's 1 millimeter here, and then this is 100 meters here. So the largest ones are obviously dikes, right? We don't have other fractures that are 10 kilometers long. But regardless, this is from the published literature and some of my own data. Apertures are never, almost never, where they are predicted from LEFM. Okay? They're always 1 or 2 orders above that. That is the dilemma that I recognized 20 years ago. And what's going on here, right? So I think the explanation for this is it's just not elastic. It is what we call creep deformation. It could be crystal plasticity. It could be solution precipitation creep. Different types of permanent strain, just not elastic. Elastic, there's not enough give there. If you were to increase the stress and put it harder apart, yeah, you get more aperture, but at the same time the fracture would propagate more. So you never go above this line here. It's kind of forbidden territory here for LEFM. So the only way of doing this is having some super soft material but doesn't exist elastically in rocks. So then the only other way is having some permanent creep deformation. Okay. So that's the answer to that for the most part. But another thing we did with Mint is, that was actually her idea, is let's look at the shape of fractures. And the thing is that continuum mechanics predicts that all fracture shapes are elliptical, regardless of elastic or not elastic. You know, could be viscoelastic, plastic. They're always supposed to be elliptical. And we said, well, let's check that. The way of checking this is there's this Lamé curve. So for an ellipse, in this curve, the parameter n here is 2. It gives you a nice ellipse. And if it is higher than 2, then you get more kind of a blunt or box-shaped aperture distribution. And if it is less than 2, down to 1 or even less than 1, it becomes more tapered. So we call it tapered, elliptical versus blunt. Okay. And she wrote a little script that where we can check aperture distributions measured in the field and in hand sample and even under the microscope relative to the ellipticity. And it turns out they have all kinds of shapes. They are really weird. You'd think this would be, looking at this, well, it's not clearly not elliptical, you know, but those are the actual shapes, you know. They are triangular, they are convex, you know, or concave, whatever you want to call this, you know. They are not even the same for the two tips at the same fraction. Yes, this is all over the place, right? So what's really going on there? This is the formation that we worked first, the Campido formation. And those are the apertures, again, 2 orders of magnitude above the LFM prediction. And this is those shape Lamé n values. 2 would be in here, that would be elliptical. You see the majority is actually less than, is around 1, more tapered, and then there's some that are above 2. Okay. So the other thing we did is we thought, let's try creating fractures in the laboratory, but not by triaxial deformation or anything like this. We would bake rock-like materials, oven, muffle furnace. And in this case we used, because my igneous petrology is not that strong, jaded and quartz. I remember this from my own class, you know. Jaded and quartz to feldspar. Stoichiometric, straightforward. And have a powder, and the key is we put a thin film of this on top of some substrate that's not reacting in the oven. So as the jaded and quartz is reacting, it tends to contract. It's called sintering. And that contraction, if it's prevented by the substrate, creates fractures. And then we did this in this dry under atmospheric conditions, hot but dry. And then we tried the same thing in a hydrothermal furnace where we have water present and more realistic for the subsurface. So for screenshots of how this works in the muffle furnace, at 900 degrees, in this case just 0 minutes, 30 minutes, 60 minutes, you see the fractures going from the outset in. So you have to go to a certain temperature before the jaded and quartz starts reacting, and then you have those fractures forming. And they form in the presence of a partial melt. So this is known in material sciences as liquid phase sintering, and it's used for industrial processes, except in that case the material scientists don't want the fractures, but we want the fractures, right? So we induce the fractures, make sure that fractures form, and those are melt ligaments. You can see how the material is being torn apart by the liquid. Actually, the liquid is a meniscus effect. It's pulling the grains together, and then when you put the grains together, at some point you have to open up a fracture, right? So that's the process there. And in the hydrothermal sintering, it's a little bit different because we have all this great albite forming. You know, it's at 600 degrees centigrade. And yes, there are fractures there. That's a fracture here. It's very irregular. It's filled with all this crystals growing into it. Then you keep baking it, and actually then the fracture starts to disappear because you fill in the fracture with all this albite growth. Okay? So it's really fascinating. In fact, the same process. It's much harder to do because you're very confined in that space of this hydrothermal furnace. So that's kind of a summary plot that Mint created for her lab samples, but also it has the Campido formation here, and then some other outcrop samples and lab samples we had. Travis Peak, I showed that already. The Boya is that geothermal, epithermal deposit. Monocratus is that rhyolite I showed in the beginning. they uniformly plot above that line, so no surprise here, but also the lab samples, right? So the lab samples are the furnace, the muffle furnace is red, and the hydrothermal sintering is dark green. They're here, so they're a little bit less open than that. And then this ellipticity, again, there's actually a pattern there that tend to be less than 2, and predominantly around 1, with the tail going to 3. Okay? So they're more tapered, and that's in the lab too. So this, what this suggests is that the reactions cause this, right? That's what all those samples have in common. You know, there's some reaction either naturally or in the lab. So why would that be? So this is a paper that we just submitted recently. It's under review. The idea is that it's a little bit tricky, actually, because again, continuum mechanics says this shouldn't exist. It should always be elliptic. Okay, I'll be smarter than all those people who do continuum mechanics, but not claiming that. But the idea is that if you have subcritical fracture propagation in a material that is not, so if it's elastic, the material recovers, it goes back to where it started, right? Let's assume the material does not go back. It's permanent strain, you know, some kind of creep fracture. The idea is that you may end up with more tapered fracture tips because this is colored by time increment. The blue one is first, and the red one, the gray one, the yellow one. It doesn't go back, it doesn't adjust. So the initial fracture had this shape, it was elliptical, but then it propagated out, and because it doesn't snap back and adjust to its ideal equilibrium shape, it has a memory of this early fracture, and it is being pushed out, but you get this tapered fracture tip because of the superimposed effects of preferred length growth by subcritical fracture, and the material not being able to recover its equilibrium shape as it would in an elastic material. Okay, and the extreme upper end, other extreme here is instead of having this preferred length growth by subcritical propagation, is that we basically just pull the fracture apart. Think about a plastic sheet with a slit or rubber sheet, and you pull it apart, and you get more or less a blunt tipped long hole, right? And the way we envision this is that there is enhanced solution precipitation creep that allows this to occur. So you have your blunting of the fracture, and that always leads to more blunting. You end up with this box-shaped fracture shape. So those end member cases here, and this would be the elastic shape, just a concentric set of ellipses. But that's not what we see, right? All right, so that's where we are after 20 plus years of working on this on and off, again, on and off. So, conclusions. I would make the claim, which is good news for those of us being engaged in this field, is that fractures will remain relevant to, even if we kind of slow down oil and gas. The oil and gas will stay, but the research money may not come in because companies are now investing in new technologies. And so we have to think proactively. And what are the new things? Hydrogen is a new thing. CCS is not that new, but it's still very relevant, right? Geothermal is a huge technology challenge. There's a lot of progress being made, but to have it large scale so that it really has an impact on our energy mix in 10, 20 years, as you see in the projections, doesn't look like it, you know, at least not now. So, but a lot of areas to be investigating fractures and faults as well. The big thing now is, I think we understand mechanical fracture growth fairly well. The big thing now is understanding the chemical mechanical interactions. Thermal eventually too, you know, but just chemical mechanical. It can go both ways. I didn't really emphasize this enough, but I talked more about chemical reactions make it easier for fractures to go, but it can actually go the other way too. And if you're really smart about it, you could actually use this to your advantage and engineer specific fracture responses based on this. So let's say you want distributed fractures, you do one type of treatment. If you do some just single fracture, another type of treatment. You know, so there may be some opportunities there. Currently, this is not something that engineers really do much. You know, there's a little bit of this, but not too much. And then, last but not least, this is kind of a takeaway here as well. I think that those large apertures and those non-elliptical fracture shapes are an indicator of the involvement of chemical reactions in fracture growth. So you could almost use this as a tool, but you could use this shape analysis and then see how much of a, how much chemically reactive this system is, in terms of its fracture growth. Well, that's all I have. Right on the minute, actually.